Now let's take a look at what a typical field-to-field move looks like. If we plot position versus time, so that would be x versus t, moves will typically look like this, where they have a starting position, say 0, and they get to the destination position. But they all look the same. No matter what you do is the way to get there, they kind of look like that. So we don't really spend a lot of time focusing on position versus time. A far more useful thing to plot is velocity versus time. And the simplest motion profile that we could show here, and one that's very easy to calculate, is what's called a triangular velocity profile. Now, if we're going a very long distance, we would typically go to a constant velocity on an x-cell, remain at constant velocity, and decel someplace over here. But when we're talking about field-to-field moves, they're short enough that usually you can handle them in a simple triangular manner. And there's a couple of simple numbers that we can associate with this. First off, if you want to know what is the time that it requires to make this move, the time will simply equal the square root of 4 times the move distance divided by the acceleration. So from that, if we plug in the acceleration and the move time, and the move distance, we can calculate the move time. Another number that's helpful to come up with is the peak velocity, V max. And that is very simple. V max is simply equal to 2x divided by t. So x is the move distance, t is the move time. And it can also be represented as the square root of the move distance times the acceleration. So that gives us a very quick way of seeing just how fast the move is at the very middle. And obviously we don't want to overrun any limitations on velocity that are present in our system. But this also helps us through the next formula to think about the power that is being used here. And so for that, it's very helpful to point out that the power in a linear motor system is going to equal the force divided by a motor constant called K sub m squared. So force divided by K sub m, the quantity squared, will be the power, and that power in the linear motor coil will be expressed in the units of watts. Now, we can expand upon this a bit, and it's very helpful to do so. We recall from Newton's second law that F equals ma. So we can rewrite that as ma divided by K sub m squared. One additional, in addition to calculating the velocity here, there's another very important simple formula for these moves, which is that acceleration will equal 4x over t squared. So velocity, peak velocity is 2x over t, and the acceleration in meters per second squared is going to be 4 times the move distance divided by the move time squared. Now notice that a is over in here, so we can now, might help to get a little more space here, we can now rewrite this formula for power to be mass times acceleration, which is 4x over t squared times K sub m, and the whole thing squared. And if we perform some of the squares here, we can simplify this to mass squared times 16x squared divided by t to the 4th times K sub m squared. So bear with us, there's a lot going on there. But there's something that's pretty important to point out, and that is the following. The power scales as the inverse fourth power of the move time. Now, humans have a tendency to just think in linear terms, and a lot of things are linear. Fourth powers are very nonlinear, and they are sufficiently nonlinear that it's hard to intuit what's going to happen. Well, let's think about that. If someone says, gee, I'd like to increase the throughput of my system, why don't we take the move time and cut it in half? Yeah, factor 2 sounds like a reasonable request. But in fact, what they're doing, if we take 2 and raise it to the fourth power, or in this case divided by 1/2 to the fourth power, 1/16, basically the motor power will go up 16-fold. So that could easily push you over the maximum power rating of the motor, at which point you go into a pretty terrible inverse cubic crash in productivity. And this is gone into in some greater detail on our website in a white paper called Slow Down to Speed Up. But in general, you have to be careful there that that fourth power really gets you. In addition, it goes as the square of the moving mass. So if you add, a kilo and double the moving mass from 1 to 2 kilos, you've actually increased the motor power 4-fold. It's not as brutal as halving the move time, but it's bad. And one way to recover that is to go to a more efficient motor whose K sub m is double, in which case you recover that factor of 4.